Alrighty guys, let's go ahead and read this lesson 1 together. So we are kicking off a new chapter. We are actually combining chapters 3 and 4 together for a chapter test that will happen the last week before winter break. So we're going to be moving kind of fast on this chapter, so we're going to want to keep up, all right? So we're going to read this first lesson today. So I need you to be marking in your text exactly what I have marked as well, okay, guys? All right, here we go. This chapter is going to be about waves. What are waves? Imagine a warm summer day. You are floating on a raft in the middle of a calm pool. Suddenly, a friend does a cannonball dive into the pool. You probably know what happens next. You are no longer resting peacefully on your raft. Your friend's dive causes you to bob up and down on the water. However, after you stop moving up and down, you haven't moved forward or backward in the pool. Why did your friend's dive make you move up and down? Your friend's jump into the water creates waves. Throwing a stone into a calm pool of water creates waves on the water surface. When the stone hits the water, the waves spread out over the surface of the water. But what is a wave? So we have our first vocab word here, so we're going to go ahead and highlight this. A wave is a disturbance that transfers energy from one place to another without transferring matter. So we're going to want to make sure that we know that waves transfer energy, but does not transfer matter. So in the example there of your friend jumping you into the pool, the energy was push through the water, and it got underneath your raft, and it lifted you up and back down. But it did not fling you across the pool, okay? So it's not going to transfer matter, but it is going to transfer energy. So what is the source of energy? Waves transfer energy away from the source or starting place of the energy. Okay, so we're going to go ahead and highlight that. So away from the source. The contact of raindrops or a stone on the surface of the water is the source of energy for the water waves. Okay, so if we, for example, we have these raindrops coming down, all right? So we have raindrops coming down. So it's going to hit the surface, and then the waves are going to ripple out away from the source of the impact, okay? So light waves also spread out in all directions from a candle. So if we have got a candle here, and then we have a flame on it, okay, the light is going to go in all directions from the source. So the burning wick is the energy source for the light waves. So we're going to go ahead and highlight a little bit in here. Light waves spread out in all directions. So in all directions from a candle flame. The burning wick is the energy source for the light waves. Energy transfer. When a stone hits the surface of the water, the stone's energy transfers or is given to the water. The energy transferred to the water produces waves. The waves then transfer energy in all directions. So it transfers to the next water particle, and the next water particle, and the next water particle, okay? So if you are on a raft in the ocean, the raft will lift you up and down by the waves, as shown in the figure below. The waves will not carry the raft in the direction the waves are moving. So similar to if you have ever been to the ocean and you are out into the water, or even a water park that has one of those wave machines. So when the wave comes, it bops you up and down and bobs you up and down, but it does not fling you to the other end of the pool or fling you to shore. Or if you're in a pool and somebody jumps in, you're going to bob up and down, but it's not going to fling you to the other end because it's not going to transfer matter, and you are matter, right? Okay, so the waves will not carry the raft in the direction the waves are moving. The waves will only move the raft up and down. So it's moving it. And so the wave passes and we see that we're right back where we started from. And then here comes another wave. And so we're going up on that all the way to the top. All right, so you'll notice that this guy here, he's not being flung to the shore. So the wave bops him up and down. It transfers energy this direction. I'm gonna make that a little bit darker. Transfers energy this way, but does not transfer matter, okay? All right, how waves transfer energy. How do waves transfer energy without transferring matter? Like all materials, the water is made up of tiny particles. When an object hits the water, the impact of the object hitting the water transfers the energy to the water, pushing and pulling on the water particles. The neighboring water particles then transfer energy outward. This energy then travels through the water from particle to particle to particle as a wave. So it comes down and then transfers energy here, which transfers energy here, which transfers energy here, and in all directions, okay? So this is if you have dropped like a stone into a puddle or skipped a stone. So it's gonna be just transferring energy out. So it's pushing on this one, pushing on this one, pushing on this one, transferring the energy, alrighty? Okay, so we're gonna learn here that we've got a couple of different kinds of waves. A water wave is an example of a mechanical wave. So I see we have a vocabulary. So I'm gonna go ahead and switch to yellow. A wave that can travel only through matter is called a mechanical wave. And I see another highlighter to highlight, so we're going to do that right now. So a mechanical wave can travel only through solid, liquid, gas. So it can only go through the mediums of solid, liquid, gas, not a vacuum. So a vacuum, not a vacuum cleaner, outer space, okay? So the material in which a wave travels is a medium. So we learned with our science short and our vocabulary on our last virtual day that everything is made up of one of these three states. Solid, where the particles are packed super tight together. Liquid, where they're not quite packed as close together so they can move a little bit, and then gas, where the particles are spread way far apart. That's going to play an important role when we talk about how waves transfer through these matters, okay? All right, so mechanical waves can either be transverse or longitudinal. So let's go ahead and highlight that. Okay, so transverse, well, let's use a highlighter, right, Mrs. Young? Here we go. Okay, either transverse or longitudinal waves. Okay, so this one right here is a transverse wave, up and down, like if you have a rope. Okay, so this looks like it's attached to a door here. So if you're just flinging your arm up and down and up and down, okay, that's going to create a transverse wave. All right, we'll come back and look at that picture again in a moment, okay? So a transverse wave is a wave in which the disturbance is perpendicular to the direction the wave travels. All right, so what that means is that when we are raising our hand up like this, the wave is actually traveling this direction. The energy is being transferred this direction. So there right here is our perpendicular, okay? So a transverse wave, and almost all of the waves are transverse waves. So we're gonna learn a few parts of a transverse wave as well as a longitudinal wave, okay? So in the figure above, the dotted line shows where the rope was before it was shaken. This is the rest position. When you shake the rope, the particles in the rope move up and down, and the wave moves forward or away from the source of energy, okay? So the particles in the rope, let's change that. Sorry, guys. The particles in the rope up and down, and they move forward or away from the source of the energy. The rope moves in the direction that is perpendicular or at right angles to the direction the wave moves. All transverse waves move like this, okay? all of them are going to have this up and down movement. Okay, so we've got a few parts on here that we need to highlight. Okay, here's a vocabulary word. The highest point on a transverse wave is the crest. Okay, so that's going to be this guy right here. All right, the top part right there. That's our crest. And then we have the lowest point on a transverse wave is a trough. All right, so we're going up and then down. And so then here's our trough. Okay. As a transverse wave moves through a rope, it makes crests and troughs in the rope. Okay, so up and down and up and down. When it's up, the top part up here is a crest. The down part right here is a trough. All right. So then this is a slinky, right? Okay, so this is another kind of wave, and this is a longitudinal wave. So I see a vocab word right away, so we're going to go ahead and highlight that. A longitudinal wave makes the particles in the medium move parallel to the direction that the wave is traveling. So if you have a slinky at home, go ahead and try this. That when you move it right here, like just pop it, you're going to see that, okay, that we're going to be moving in this direction. We don't have any of this, okay? Nope, that's a transverse wave. We have a longitudinal wave here. So as we push it, we're going to have places that are closer together and places that are farther apart. So the back and forth movement of the hand on the left produces a longitudinal wave that travels to the right. Okay, so if you push it here, the wave's going to travel this direction. You push it this way, if you push it again here, it's going to travel back. Okay, so if you have a slinky at home, go ahead and play around with that for a little bit. Okay, all right, so the figure above shows a longitudinal wave. Longitudinal wave, we're going to go ahead and start that right now, understanding that that is a sound wave. Okay. Okay, the figure above shows a longitudinal wave moving along a spring. As the wave passes, the coils of the spring move closer together and then farther apart and back again. This is parallel to the direction, okay? So it's not perpendicular. This is parallel to the direction that the wave itself moves. Okay, so we're going to go ahead and mark that here, that this is parallel, okay? And we could come up here and we could mark that this is perpendicular. All right, so this is your right angles. Okay, that's going to be important for you, to understand and remember, okay? All righty. So we've got some parts on this wave as well that we are going to need to learn and mark. Okay, so I'm going to jump down here and highlight the words, the region of a longitudinal wave where the particles in the medium are closest together are the compressions. The regions of a longitudinal wave where the particles of the mediums are farther apart are rarefactions. So before a wave moves through the spring, the coils of the spring are at the same distance. So if you just have a slinky sitting on the ground, there's no energy in it. The coil's going to be all, spread about the same amount. This is the rest position of the spring. This changes when a wave moves through the spring. The wave produces regions in the spring where the coils are closer together and than they were in the rest position, and regions where they are farther apart. All right. So right here we can see it's closer together. So that's going to be your compression. And then I'm going to come down here and mark this rarefaction. You see where they're farther apart, okay? So there's a rarefaction, there's a rarefaction. Here's a compression, here's a compression. Okay, here's a compression, here's a rarefaction. Okay, so where they're closer together, and then where they are farther apart. Okay, so these are going to be terms that we're going to be talking about a couple of more times as we talk about wavelength, as we talk about amplitude and energy. All right, okay, so vibrations and mechanical waves. When you hit a drum with a drumstick, the surface of the drum moves up and down or vibrates. Vibrating objects are the source of energy that produces mechanical waves. Okay, that's super important to know. All right, so we'll go ahead and highlight that. Source of energy that produces mechanical waves. So just like if you hit a drumstick one time, or if you hit a key on a piano or strum once on a guitar, one wave is going to be one vibration. Okay, so imagine that you are making a transverse wave with a rope. Each time you move your hand up and down, a single vibration occurs. One vibration produces a transverse wave with one crest and one trough. So if you just move your hand up and down one time, if we come up here and we look, we just go up and down, we're going to produce one wave. That's it. And then we're going to go flat again. Okay, so if we look here, this arm went up and down a couple of times to produce a trough and a crest and a trough and a crest. Okay, so if we just have one vibration, we're just going to have one wave with one crest and one trough. Okay, alrighty. So vibration stop, the wave goes. So what happens when you stop moving your hand? No new waves are produced. The waves that are already moving through the rope will continue moving through the rope. Okay, so if you move your hand, if you stop with the slinky, that energy that you created from creating that wave will carry down the slinky, but it will eventually stop. Okay. All right, so it just won't keep going back and forth, back and forth. You've got to keep adding energy to it. All right, so types of mechanical waves. All mechanical waves travel only in matter. Wow, is that going to be important for you to remember? Only through matter. Sound waves. So this is going to be a part on a study guide that you're going to get next in-person day. That's going to be a part on your study guide. So sound waves, water waves, and waves earthquake are mechanical waves. Okay, so we're going to go ahead and put a little star here, and this is going to be on your study guide, just so that you can find it easily. Sound waves are longitudinal waves that travel in solid, liquid, and gases. Water waves are a combination of transverse waves and longitudinal waves. Earthquake waves are also seismic waves. They are both longitudinal and transverse. Seismic waves. But except for those, things are going to be just a straight longitudinal wave like a sound wave, or a straight mechanical wave like a transverse wave. So we only have a couple of examples here where you're going to have both of them being used at the same time. Okay. All right. So this finishes up this little section, and this is on EM waves. Okay. So I see a vocabulary word. We'll go ahead and highlight that. An electromagnetic wave is a wave that can travel through empty space and through matter. Okay, so this we are going to abbreviate EM. We touched on this last chapter with radiant energy, and we had talked about that with our microwave waves that are used with our cell phone and with our actual microwave ovens. Okay, light from the sun is a wave, but it is not a mechanical wave. A mechanical wave cannot travel through space from the sun and earth. Light is a electromagnetic wave, okay? So let's go ahead and highlight that. That light is an EM wave. So an EM wave is a wave that can travel through empty space and through matter. So it can go through solid, liquid, gas, and empty space. So let's write that down. So it's going to go through solid, liquid, gas, and empty space. So empty space is also known as a vacuum, right? Okay. So the types of EM waves. There are other types of electromagnetic waves besides light waves. So here are all the EM waves, all right? So we're going to talk more in depth about that a little bit later. But radio waves, microwaves, infrared waves, ultraviolet, okay? And we also have X-ray goes in there, and we have gamma that also goes in there. So every object gives off electromagnetic waves. The type of electromagnetic wave that an object gives off depends mostly on the temperature of the object. Objects near human body temperature give off mostly infrared waves. So that's where you have those night vision goggles are utilizing that infrared wave. EM waves from the sun. Like all waves, EM waves carry energy, okay? So we're going to go ahead and mark that. So waves carry energy. Just plain and simple, waves carry energy. So our EM waves are also going to carry energy. Scientists often call this radiant energy. Infrared and visible light carry about 92% of the radiant energy that reaches Earth from the sun. Ultraviolet carries about 7%. So that just leaves a little bit for the other ones, right? Okay, so we're going to have much more talk on EM waves. So this was just a really quick introduction to them, all right? So make sure you have everything marked. Now what I want you to do is I want you to work on your vocab. So you are going to work on getting these vocab words done, okay? All righty. Hang in there. Reach out if you need anything. Bye-bye.